Alex approached me and asked me just to kind of set the tone for the day and hopefully give you something to think about for the rest of the day. And what we came up with was basically a kind of how do you understand all of this cloud native storage stuff? There's a lot of technology, there are a lot of competing products, there are a lot of different approaches, there are a lot of buzzwords flying around, and not all of them are very well defined. And so it's sometimes useful to kind of build a mental model for yourself where you can start hanging all of this information that you gather at places like this in some kind of coherent structure so that it all makes sense. And also so that you can have conversations with people. So sometimes if you both have a tree of knowledge that has approximately got the same branches, you might have, different Christmas decorations hanging off your tree, but at least you have this similar tree and you can, put them next to each other and say, your one's got more red Christmas decorations than my one, which has green ones, but we're talking about the same language. So that is kind of broadly speaking what my goal today is. There will be some time at the end as well to discuss, ask questions. So you even welcome to interrupt me along the way if there's something that you think would be better addressed on the spot than waiting to the end Q&A session. I will not be offended if you interrupt me. All right, so with no further ado, oh, that's interesting. It's cut off on my screen, but it seems to look good for you guys. Okay, so there's this buzzword about stateless applications, and I'm not going to waste our time today debating what actually the definition of a stateless application versus stateful application is, because I don't think that's productive. But suffice to say, the vast majority of useful applications store data somewhere, sometime. And whether you call them stateless or not is kind of academic, but what you shouldn't assume is that you can write applications that don't store state anywhere. Because it is possible that they do exist, but they're by far in the minority. So rather than pretend they don't exist, let's understand like what the different kinds of state are, how they can be stored, what the pros and cons are, etc. Another myth, which I think is fairly prevalent, is that there was storage in the old days, and we had all the storage vendors, and we had very expensive pieces of equipment in the corners of our data centers, and those were very successful for a long period of time. And then along came the cloud, and then suddenly all of those things were not useful anymore because this is the cloud and everything's wrong. And that I don't think is an accurate depiction of reality. I think there are many, many different ways of storing different kinds of data, and almost all of them have some place somewhere as being a good solution to a given problem. It's not the case that there is any single solution that solves all the problems, and many of them have pretty significant downsides in particular areas. And a lot of this came along as a result of, life was fairly simple in the early days. You had typically either a local disk on a machine or some kind of filer in the corner or a database. And, for the most part, you could use one of those three things. They all looked roughly the same. Relational databases were mostly approximately the same. File servers were approximately the same, and local disks were approximately the same. And so you just picked between one of those three things, and it worked as well as it worked, and life was simple. Then along came, the internet generation. And all of a sudden, applications changed pretty fundamentally. So you had gazillions of users. They all expect free infinite storage, instant response, 100% uptime, and nothing ever gets lost. And that all seemed pretty reasonable because that's what you want. And it turns out that providing that, or even an approximation of that, is like really, really, really hard. And that's hopefully what I'm going to give you some structure upon which to sort of build your knowledge base today, so that it makes a little more sense. Like, what is this? What are all the problems? What are all the potential solutions? What are the pros and cons, etc. So along came Storage Man, Cloud Storage Man. So he was going to go and solve all of these problems. Cloud storage is cool. We've got all these great new cloud native databases and cloud native block stores and object stores and everything else. And life is good. All of these problems are going to go away. We're going to provide all these gazillions of users with infinite storage that never goes down and never loses their stuff, and it's free. Turns out not so much. So there are many, many different options. They are suitable for different use cases, and what I find personally useful, and just a bit of a kind of an aside, I'm not actually a storage expert at all. I don't know very much about storage, and I don't know much about networks either. But somehow I seem to have ended up designing, like a lot of the early networking in AWS was kind of me. I couldn't even spell TCP, but I figured if you start from scratch, you pick up an O'Reilly book and you find out how TCP works out. How difficult can it be to actually build a software-defined network? It can't be that hard. And EBS was actually a similar story. We were like, oh, we need to provide disks. They can't be local because they mustn't fail with the virtual machines. So we'll just build something on the back end. We can't afford, enterprise storage systems because they're too expensive. So we'll just build our own. That can't be very, very difficult. And so we built EBS and S3 and things like that. So despite my history, I don't really claim to be a storage expert. And I'm sure there are many people in this room who have far more experience than I have with storage products, storage projects, hardware, technology, etc. But I do have a reasonably sort of decent high-level view of what the problems are and some of the trade-offs. So hopefully that can help some of you. So the key things I think that are really useful are to actually get a detailed understanding of what some of these fundamental attributes of all storage systems are. So things like availability, scalability, performance, consistency, durability, complexity, and cost. And these are all, buzzwords that get thrown around all the time. But I think if you go and ask somebody what exactly one of these words means, you'll find that there's a diverse set of opinions, and in fact, a lot of people who assume they know what it means until you ask them to explain it. And then they realize they don't really know it. So that, hopefully we can dive into some of those today. The other thing, the flip side of that is, what does your application mean? Once you realize that there are, at least 7 of these properties, and each one of them you can actually break down into different categories. Scalability is the scalability of the number of clients, the scalability of the amount of data you can store, the scalability of the volume of data that you can process, that you can read, write. These are all very, very different things. They all sort of fit under scalability. But then, understand for your given application, which set of these attributes do you really need? You can't have all of them. I think people are starting to understand that. Things like the CAP theorem have kind of educated people a little bit that there are some fundamental trade-offs that you have to make. So you can't have all of them. So which ones do you want the most? And I think also, things like pay-per-use, EBS type storage have educated people that you can, and in fact free storage like YouTube and these kind of things, you can actually get vast amounts of storage free of charge. So if you're going to, want stuff that free storage doesn't provide, what exactly do you want and how much are you prepared to pay for it? Not only in terms of money, but in terms of availability, durability, and various other of these properties. So once you understand your requirements properly, you can then map them to your now vast understanding of the landscape of cloud-native storage, and you're off to the races. So just diving a little bit more into these attributes, as I mentioned, I think it's pretty important to understand what these things mean, how they get achieved, and some of the subtleties underneath them. They're not always as simple as the terms might imply. So availability tells you about, what the uptime is, what percentage of the seconds in a year can you read or write your data. And those two answers might be different. You might be able to read it all the time and write it none of the time or some of the time. But figuring out exactly what those numbers are is pretty critical. And there are vast differences between some of these products. I mean, you will find projects and products that, don't guarantee more than 99% uptime. That's like a lot of the time you won't be able to get to your data. And in some cases, that's fine. In other cases, that's catastrophic. Others, I saw the marketing blurb for S3 the other day, not actually to do with availability, but the durability was claiming like 11 nines durability or something. So I mean, there is a scale, a vast scale of these attributes. The other thing that's worth understanding is, what exactly are the failures that can make your stuff unavailable? There's this sort of a small set of these categories, or a small set of failures that people kind of understand. Machine goes down, power failure, storage is gone. Like, is it available somewhere else? Or data center gets blown over by a hurricane, like all the drives in the data center are offline, storage is gone, or at least temporarily unavailable. But it turns out that the probability of those things happening is vastly different. And there's a whole bunch of other failures in between that people think about less often. Like, we upgraded the operating system and it failed and all the software crashed, which is, very different than a hard drive failing or a power supply failing or a data center being blown over. Also, the percentage doesn't tell you everything. If something becomes unavailable every day for a minute, that might give you some number of nines of availability. But that's very different than it being available for 3 years and then disappearing for 3 days. That's a pretty bad situation. It's also, give or take around about 3 nines. But it's being gone for 3 days is a lot worse than being gone for a couple of minutes every day or every other day. The other, which gets to mean time to recovery, like if these failures do happen, how long does it take to get the stuff back online? Scalability is another area, and I don't want to bore all of you. I think some of these attributes are reasonably well understood. My point was just to get the idea across that there's quite a lot of detail under here, and it's worth diving below the surface. Scalability. So how much data can be stored? That's pretty obvious. Everybody thinks about that. How many concurrent users can it support? Depending on the architecture of the application, it's not, in the good old days, you had every user had a desktop application, had a connection to the database or a connection to somewhere. Now, users and connections are very different, but the problem remains. You need to understand the architecture of your system to understand how many independent connections you need to whatever storage system it is, and what the properties of them. Are they read connections, are they write connections, etc. How fast can you read and write? There's often a very big difference. And most importantly, if you miscalculate what the requirements of the application are, and everyone dreams of having, one of these exponential takeoff startups where, there was actually quite a fun story in the early days of EC2 when we started that. There was a guy, I still remember his name, I think it was Mikey. And he had a little startup. He might even still be around, and my apologies if I'm telling the story without his permission, but he came to us. We were still, pre-release, limited alpha. And Mikey said, oh, by default, we gave people like 10 virtual machines and a couple of disks. And he called us up and he said, oh, he's got this thing, this video rendering thing, and it basically takes all your photographs of Facebook and your favorite music, and it bundles them all together into this cool, like, pulsating cube thing that you can then show to your friends and put on your Facebook page. And it turns out it's become quite popular. He was running it on his 10 virtual machines, but they're not enough, so could he have like 500? So we said, that's not, we've only got a few thousand. It's like a few weeks after we started previewing this thing, but sure, you can have 500. And he called us back about, 12 hours later. He's like, "Could we make that 5,000?" And we said, we have to turn on some more racks for you, but sure, 5,000 we can do it a stretch. Glad that you're having success. And I think the next day he wanted like 28,000 or something. So these are stories. They do happen. You've probably ran across or heard about that whole Angry Birds thing. I was at Google at the time, and they were running not Angry Birds. Angry Birds was actually that was a different Google story, but Pokemon. So Pokemon was running on Kubernetes back in the day, and similar sort of thing. It just went from nowhere to many hundreds of millions of users in literally overnight. So that being a diversion, the question is, like, if any of these properties these attributes you selected, you said, right, on day one I need attribute X, Y, and Z, and I need this amount of scalability. What if you got it wrong by like 5 orders of magnitude? What options do you have? And are they reasonable options? That's pretty important in some cases, particularly if you have the kind of applications where very rapid growth is a possibility. Performance is a pretty obvious one. So latency, how long does it take between when you're trying to read or write something and you actually successfully complete the operation, which is different than throughput. So if you send a million operations to the database or to the storage system, how long does it take for all million of them to succeed, which is obviously different than latency. And there are many other kind of attributes or parts of performance that are worth understanding. Consistency is one of my little pet peeves, and everybody I think these days is familiar with NoSQL databases versus ACID and all this kind of stuff, and that's all very well. But it turns out that consistency is a way more complicated topic than most people appreciate. So how many in the room have heard of the CAP theorem? Right, and what does the C in CAP stand for? Consistency, excellent. And how many people in the room have heard of ACID? ACID transfer. Everybody's heard of ACID transfer. What does the C in ACID stand for? Consistency. Are the two the same? They're completely different kind of consistency. You can barely compare them. So there's just one example. And then within consistency, how many people know what serializability means? Okay, a smaller number. And there are like another 10 of those words, and I guarantee you that every word I mention, the number of hands will drop. And everybody had heard of CAP, and everybody had heard of ACID, and everybody knew they stood for consistency. But actually, few people appreciate like exactly what that stuff means. And so before you say, oh, this is a consistent database, it's worth understanding what exactly that means. It means very different things to different people. Generally, it means something along the lines of, in the context of cloud storage, it means how soon after you write something will everyone read that stuff? And even that question is kind of loaded with a whole bunch of, if I read it, do I get what I wrote? Because that might be important if I'm processing a transaction or doing, any sort of online thing. It may also be important for other people to read that data very soon after I've written it, or not. Sometimes they can, eventually consistent. But these are very important considerations, and they can be the difference between an application working and not working at all. I was actually just telling a story the other day, last night, that I was waiting for some, messages to come through on my phone, and didn't get these messages. Turns out big problem because these messages never came through. And I got back to my hotel room, and all my messages were on my laptop. They had, they were eventually consistently going to land on my phone, but just the next day. I won't mention who the vendor of said messaging system was, but there's probably some representatives in the room. And the other question is, when do these things actually get committed to non-volatile storage? So in many cases, you can have, a durable write transaction that succeeded. And for the most part, unless something dies in the next, minute or two, your data will be safe. But depending on, if you have very large systems and you have thousands of machines, the chances of none of those machines failing in the next minute turns out to be very low. And then if you have an entire rack go down, which tends to happen quite regularly, actually, power supplies fail, various things happen, you lose like 100 machines at a time in one fell swoop. If both of your transactional copies happen to be in that rack, you're toast. Your supposedly durable data that you religiously stored on 3 disks is actually not committed to the disk yet. It's still stuck in the cache, and they all lost power, and it's gone. And durability is a similar. There's some overlaps between some of these attributes where it's difficult to tell whether this particular issue is more about consistency or more about durability, but you get the idea. There's another big one, and some of the Upbound guys and people in this room have written operators to run various storage systems. So how do you actually instantiate, deploy, and use this thing? There are vast differences between various of the offerings. Obviously, you have, on the one end of the spectrum, you have public cloud providers who do a lot of the instantiation, deployment, etc. for you, and you just consume the stuff, usually via some kind of an API. But if for whatever reason either those particular offerings by public cloud companies don't qualify against all the attributes that we mentioned earlier, or you're running on premise, or many reasons, you might end up having to instantiate, deploy, and manage these things either yourself or hire somebody to do it, or write software to do it, or buy somebody else's software to do it. So that's pretty important. And then, overlapping with this is how portable are your applications? So if you're writing an application that reads, files and writes files to this magic, file store in the sky, you can pretty much take that and run it anywhere. You can run it on your local machine against your file system. You can run it against your NFS server, and you can run it against, various different distributed file systems. And for the most part, it'll work fine, and you don't have to go and rewrite your code. However, if you write your code against some API, whether it's a S3 storage API or any other proprietary API, unless you're very careful, and it is possible to design systems that are well structured and can be moved easily between storage backends, more commonly your engineers will take the shortest path to getting something working, and then when you try and move it somewhere else, it ain't going to work. And you're going to have to, do various degrees of major porting versus rewriting the whole thing. So just be careful of that. And another obvious, fairly obvious one is cost. What kind of cost is it? Is it pay-per-use cost? Is it, major capital expenditure cost? Is it based on mass-produced commodity components, be those software or hardware, or is it specialized stuff? In some cases you get big benefits from specialized hardware or specialized software, but they do come at a cost. Usually, smaller production volumes, lower economies of scale, etc. Some kinds of storage have, very different degrees of redundancy built into them. So many of you will probably be familiar with S3 and object storage. And I don't know, I actually haven't looked behind the covers recently, but certainly in the early days, it was designed around having, 3 copies of the data, 3 full copies in different data centers, or at least 2 of them in a different data center than the other ones. And the data transfer costs and the actual storage volume that is used is massive. And if you've got very large volumes of data to store, and you're multiplying the cost by 3, that can make a big difference to the bottom line. On the other hand, things like erasure encoding and RAID and things like this can reduce your amount of wasted data to a much smaller amount, but they come with their own set of trade-offs. Right. I'm sensing that I'm boring people because there's some glazed eyeballs in the audience, so I'm going to change gears a little bit here. So the other interesting aspect of all of these storage technologies that we run across in a cloud native environment is the topologies. And people tend to focus on the API. So this is an object store, this is a file store, this is a key value store, and this is a database. But it turns out that doesn't really tell you very much about the actual attributes of the storage. In some cases, people imply them because, well, S3 was called an object store. As I keep using S3 because it's kind of one of the granddaddies of cloud storage. But it happened to have been designed around storing large objects and having an API that's sort of HTTP driven and being low cost and very high durability. You had these 3 copies that I mentioned earlier, and your photographs of your grandmother never go away, all of that stuff. But that isn't actually fundamental to an object store. And it's entirely possible to build an object store that has exactly the same API as S3, but doesn't have any of those properties. It doesn't have any of the durability guarantees. It doesn't have any of the similar latency properties, etc. as S3. So it's very important to understand what the different topologies are that you can build these things on, and how these topologies influence those basic attributes that we spoke about earlier. So in particular, cloud native storage typically is either a distributed system of some sort that may be sharded, so you might actually split the data up based on a key and spread it across a bunch of shards. It could be converged, so hyperconverged is a buzzword that's floating around. So is your storage and your compute capacity for your cloud, is it on the same machines, or do you have actually distinct machines? You have storage boxes and compute boxes, and there are pros and cons to both approaches. Is it centralized or relatively centralized? So do you have like a small number of boxes in the corner where all your stuff is stored, and those boxes usually are fundamentally different than the ones your compute jobs are running on? Or is it completely sharded out or distributed across your data center? is it local? I mean, there is actually a use case for, at the end of the day, all storage ends up on hard disks. Hard disks typically sit in machines. So somebody's got to have local disks somewhere along the line. Otherwise, you ain't got no storage. And more commonly, they're a combination of all of these different things. So I wanted to speak just a little bit about exactly what these topologies are. We'll give them some names. You can call them other things, but as I mentioned earlier, to have useful conversations about some of these topics, it's useful to have a set of terminology that everybody commonly understands. So for centralized storage, we have a small number of storage servers, typically tightly coupled, so they have some sort of shared state. They're usually, in fact, often tied together with proprietary storage fabric of some sort, specialized hardware, usually for high availability, performance, and scaling reasons, because they don't have some of the other tools available to achieve high availability, performance, and scaling. So they use some of these pretty fancy pieces of hardware. They usually, when you need to scale them, when you need more of some attribute, performance, volume of storage, etc., you usually have to get bigger boxes. So you start with 2, a master, a slave, or whatever, or maybe 3, and then if you need more, you just replace them with bigger boxes. It tends to be quite expensive and quite invasive, but it's possible. And they don't scale out very well, so you don't just get large numbers of these things building up in the data centers, because then you end up with a bunch of problems which we won't talk about now. We're a little short of time. How am I doing here? I think I'm 30 minutes in. 10 more minutes and then we open for Q&A. Okay, cool. Where were we? So one of the benefits of these centralized storage systems is they often provide very good performance, very low latency, and very high levels of consistency than many of the alternatives. So if those are the things that you need, you shouldn't necessarily go shopping somewhere else, or you should consider these as viable propositions for your use case if those are the most important attributes of your use case. It doesn't help if you have something that needs highly consistent, high performance storage. It doesn't help to go and look in the bucket with very low consistency, very low performance storage, because everybody's like shopping in that bucket because it's cool. It does have benefits. It scales out, it's cheaper, etc., but it may not actually do what you want it to do. So scale up can be very challenging with some of these systems, and I'm speaking broadly here. These are not like digs at any particular vendors. These are just my observations. As I mentioned, I've never worked for a storage vendor before. I don't really know all of the detail of this stuff. It's just my observations, and the reasons why many of these cloud type storage systems have been built is to address some of these issues. So scale up can often be very challenging. There's only a certain size box. If you are a Google or an Amazon, or I was talking to a bank the other day, was saying similar things. If once you go beyond, the sort of edges of the bell curve, it becomes impossible to scale. There aren't big enough boxes. They don't exist. And failure handling can be pretty challenging. So, many of you have come across like two-phase commits and these kind of things. Many of them don't actually work properly in a fully automated fashion. So when you have failures, you actually have to have humans come in there and fail over machines, and it can be very, very painful, and people get woken up in the middle of the night. And these are not, it's not like the storage vendor did something very bad. You just can't do any better than that with a master slave setup. Like, it's just impossible. And so they have these challenges. Now, along comes distributed storage, and I use these words typically and often a lot in this part of the talk. None of these are black and white rules for the most part. They're more an observation of what the generalities are. So these distributed storage systems typically have large numbers of commodity nodes. They tend to be much more software focused than centralized storage. Centralized storage is a lot about buying big pieces of hardware with fancy gear in them. Distributed storage is more about buying or getting often open source software that runs across your commodity nodes and provides you with some or other approximation of what some of the alternatives might provide. Data is synchronized usually across commodity networks. This is TCP, etc. It wasn't designed for storage. It wasn't designed for high consistency data communications is actually designed for completely different things. They tend to focus much more on scale out than scale up. So it doesn't matter what size boxes you have. If you need more storage capacity, more performance, etc., just buy more of them. Buy thousands of them if you need to. And the theory is that you get all the scaling. Now, along with that comes, how do you deploy these things? If you've got thousands and thousands of these nodes running, and they're all running open source software that gets patched every other week, because that's what we do with open source, we change it all the time. Then how do you actually run the stuff? How do you upgrade your thousands of nodes? How do you make sure that your storage doesn't go offline while it's happening? And so there's a whole industry that's developed around building systems that will manage these things for you. They may support traditional access methods, so iSCSI and block-based systems, NFS for files, etc. But often those protocols themselves, like deep buried inside those protocols, they were designed for accessing local files on local disks. And so as soon as you stretch them across a network, and particularly across a distributed storage system, you end up with very odd things happening sometimes, and sometimes very suboptimal performance behavior. So many of them also provide APIs, native APIs to those storage systems that are very specifically designed to access that kind of storage and don't suffer from all the shortcomings of traditional block APIs. But those again are less portable and much more invasive into application code. Usually you have to bind all sorts of libraries in to make use of these things, or in the case of Kubernetes, you might have some sort of sidecar pod or something which is used to access the storage, but it makes everything a lot less portable. Sharded storage, I think I'm going to start skipping over this, but most of this is pretty self-evident. So you partition your data store, whether it's blocks or files or key value pairs or any other kind of data. You use some sort of hash function. You decide which one of the shards this hash falls into, and then you go and execute your reads and writes against that shard. Now, a shard might be a physical machine or a whole bunch of replicated machines, but it's a good way of scaling out horizontally. So if you want more capacity, you just create more shards. You just change your hash function and everything's good. The problem is, one, the sharding function you need to use is very dependent on the actual data. So depending on what the properties of your data are, you don't want to you don't want to end up with all of your data being mapped to shard number 1, because in your world, all your customers' surnames start with A. So, you have to custom design some of these sharding functions to make sure that they spread evenly. And then even more problematic is the fact that your data changes over time. So, when you deployed your stuff and you designed your sharding function, you had a nice spread of customers from A to Z, but then, over time you moved into Azerbaijan, and there are lots and lots of people there whose, last names start with T, or whatever it is. I'm not Azerbaijani, so I don't really know. But you can understand the problem. Now you have this, okay, so they're all landing on the same shard. Now we're going to reshard all our data. We're going to move all the data from where it is to somewhere else in real time, online, while everybody's accessing the system. Big problem. So worth bearing in mind. And then even worse than that, sometimes that's just too difficult, so people just don't do it. So you get what I've just made up a name called shard rot, which is that you just end up with unbalanced shards. Your performance of your system goes down. You run out of capacity because you've got all these half-empty shards, but it's just too much trouble to move everything around and balance it all as frequently as you need to. So yeah, rot. Hyperconverged storage, I'm not going to go into this. I think it's pretty obvious. I guess the pros are, you buy one kind of box. The box has got compute capacity, it's got storage capacity, disks or whatever, and you just buy more of them. As your compute load increases, so you just buy more of these boxes, you get more storage, and as long as everything kind of works out all right, you're okay. It's very flexible because you just got one kind of box to manage. You don't have to configure them differently. They're all configured the same, and there are many organizations that do this, but it does have some problems. If your workload characteristics start moving more towards needing more data capacity, there's storage capacity and less CPU. Maybe you put GPUs in your machines or something. So now the percentage of your CPUs that are used is much smaller. And now you've got lots of CPU and not enough storage. But you have to buy more of these boxes because you need storage. You don't need the CPUs, but you're paying for the CPUs anyway. So you end up with various problems like that. You also can have interference. So if you have very, very CPU-intensive applications running on your nodes, it turns out that your storage system needs some CPU as well. So if there isn't any left for it, then your storage suffers because your compute workloads are using up all the CPU. So in other cases, it's better to have different flavors of boxes, storage boxes, compute boxes. When you need more storage, you buy more storage boxes. When you need more compute, you buy more compute boxes. Much simpler. I think that's most of what I want to talk about there. There's sort of this bad rap that local hard drives get, particularly in the cloud computing space, and I think I can perhaps claim some responsibility for that. When we launched EC2 in the early days, we had very humble machines, and you got a half a disk, I think we gave you with your virtual machine, and it turns out that that contended with other users, and performance was bad. And then people sort of said, well, you should just never use local disks. They're useless because they can fail and go away. And what use is a disk that can fail and go away? And that's not entirely true. So it is true that local disks in a cloud computing setting do share the fate of the computational capacity as well. So when a machine loses power or fails or whatever, you lose the disk and the CPU, and that's all very valid. But it turns out these things are super valuable for as building blocks for distributed storage systems. So obviously all of your fancy distributed cloud storage systems, they still need to store stuff on disks. So if you're trying to build one of those, you really want local disks. Turns out a lot of workloads themselves actually need local storage too. They need caches, they need read-only data. Things like Google Search and Google Ads. I used to run some of those things at Google a while back. So a lot of them work on the basis that there's some pre-processing. You go and trawl the whole internet, and you go and index everything, and you go and work out what it is you need to serve up, and then you just load that stuff onto the local machine, and it might take hours. And then you start up the thing, and everything reads off the local disk. And if it gets lost, who cares? Because you're going to start it up somewhere else and reload it somewhere else. So that those are cases where you definitely need storage, and you don't want that storage to be remote somewhere and be incurring data transfer costs across the network, and maybe that remote thing is duplicated and replicated because that's what most people want from a remote store. I don't need any of that. I just want it on one disk locally, and I want to be able to read it really fast. And when I die, my storage can die with me, and I'm happy about that. It's very inexpensive. It's often very high performance, low latency, but if you share these disks with other workloads, you can run into trouble. My little plug for the humble local hard drive. They're not all bad, and they're very useful in many cases. So I'm going to talk for another small number of minutes. So I just wanted to touch on, sort of the architecture of storage stacks in cloud computing. And I think this diagram, what's in it, is familiar to many of you, but it's worth sort of bearing in mind that you have different layers in the stack. Often these layers, we spoke about topologies and attributes or properties earlier. Each one of these layers can have different topologies and different storage, different attributes. And when you layer them on top of each other, things get even more complicated. So right at the bottom, you typically have a storage system, something that puts stuff on disk, and you have a data access interface to that. That may be via an API and maybe directly. So your workload running in a container or pod in Kubernetes, might actually create a connection directly to a remote data store of some sort via the API. Or in other cases, they're exposed, for example, via volumes, file systems, block stores, etc., through the container interface. And that's what our control plane interface looks like there. So this is the software that plugs a volume into the bottom of your container, and that volume may be a remote volume or a local volume. And then we have a bunch on the bottom left there, a bunch of frameworks and tools. So things that help you, as I mentioned, a lot of these distributed systems and non-traditional storage systems are complicated. There are many of the nodes that run these things. They have complex interrelations, and they change quite fast. So you often need automation to help you run these things, to install them, to upgrade them, to monitor them, etc. It's much more complex than a pair of storage servers sitting in the corner of your data center. I think I've spoken about that. There are different data access interfaces. The access interface does not define the properties of the storage. It just tells you what the interface looks like. So beware of that. Just because something's called an object store and because it has an interface that looks like S3 does not mean that it does the same thing as S3. It may not create the same number of copies. It may have completely different performance attributes and various other things. So don't fall into that trap. And the same applies for everything else. I've seen many examples of user-level fuse file systems sitting on top of etcd, sitting on top of remote block stores, and oh, it's a file system. It's just like NFS. It's not just like NFS. It's completely and utterly different, completely different properties. So don't fall into the trap of honing in on a single word and saying, oh, that's the same as that, because they both have that word in them. You have to, unfortunately, dig under the hood and understand what's going on down in the depths. So the API, the takeaway, I guess, is the APIs don't determine any of the attributes, or indeed very much at all. I've mentioned some of the trade-offs. I'm not going to go into that. And we can skip over a lot of this. So here, I had a little bit of stuff I was going to talk about, key value stores. I think the takeaway here really is that here's another example. People read key value, they know what a key is, they know what a value is, they've heard of etcd, they've heard of zookeeper, they've heard of chubby. They think, oh, they're all like that. Key value stores look like that. Completely not true. Many different kinds of key value stores, many very different properties. And I think it's very important to, and here's an example of a bunch of different flavors, and I've deliberately not mentioned particular product names or project names or vendors or anything here, simply because I think it's worth knowing. You actually do get local key value stores. There are many of them, BDB, etc. you might know of. There are many remote stores. Those are not necessarily distributed, not necessarily replicated. Then you get distributed, non-transactional, replicated key value stores, and those have a bunch of availability, scalability, consistency, durability, performance attributes. And then you have distributed global transactional stores, and those have a completely different set of properties. So make sure you know what you're talking about. And finally, I get to the end. People are looking very bored. I think I've spoken for too long here. Some parting words. If all you remember about this talk is the few things on the slide, then hopefully you've learned something. Know your fundamental attributes. So understand the scalability, performance, availability, durability, etc. of whatever it is that you're looking at. Don't believe everything you read. Go and actually look under the hood, get some numbers. Like if you want a certain amount of performance, go measure the performance, or get someone who's measured it. Don't say it's high performance, or believe somebody who tells you it's great. Get some numbers, like how many IOPS does it do? How many clients have you actually connected to it, and what is the performance of those clients, etc. And then understand the requirements of your system. Your requirements of your application are not, I want the best storage possible, give me the best one. Doesn't make any sense. Understand it exactly in terms of the fundamental attributes that you need for the application that you're developing. And many of them are very different. If you're building a massive messaging system, you have latency requirements, you have scalability requirements if you're a WhatsApp or a WeChat, which are very different than a high-value banking transaction website, which might have much lower transaction volumes, but the individual transactions are way more important than the IM messages that you send on WeChat. Or not, depending on what you're trying to do. Try and understand the unavoidable trade-offs. Some of this stuff is not, this vendor is better than that vendor, or this project, this open source project is just better than the other one. Some of these are unavoidable trade-offs. If you have distributed transactional storage, you have some fundamental latency that is sort of defined by the speed of light that you cannot get around. So make sure you understand what those are, and don't fool yourself into believing that they don't exist, because they do. And pick the best tool for the job. That's it for today. Thank you very much. I'm Quinton.
You've left yourself open for 5 minutes of questions. Are you okay taking some questions? Yeah. Okay. Do we have the other microphone? Because I want the questions to also be part of the recording. That would be awesome. Does anyone have a question for Quinton? Wow. No, it was very educational. Seriously, no questions? Okay, well then, okay, we do have a question. Hang on, the mic is, Joseph is running. Thank you, Joseph. Pass that forward, please. And let me give it, I don't wish to.
Hi. I come from the visual effects industry, and I was part of the CXFS beta program, and I'm wondering if you had run into interesting stories about data consistency issues and how you recovered from them.
Not in that industry specifically. Maybe you could just give me a little, I'm not familiar with all of those acronyms you mentioned.
Sorry, XFS has been open sourced, I think, and so CXFS was the distributed XFS file system.
Okay.
And then there was some early instances where there were consistency problems with checksums. And so the recovery was quite an ugly, difficult thing. It happened on Christmas Day, and I was just curious if you had another story that was to do with data consistency and how you recovered from it.
Did you mention that was in the media industry, or okay? Not off the top of my head. There was a very interesting story way back at Amazon days, which doesn't directly relate to your particular file system, but good Lord, I'm going to have to just try and refresh my memory now. So there was some very low probability CRC check collision where these things were distributed by UDP, I think, and UDP had I think it was like a CRC13 checksum with each message, and these things were used to propagate the index for some or other big global storage system. And you can do the math, you can figure out what the probability of some bits getting corrupted in an index UDP packet, and the CRC check still checking out fine. So this stuff got sent around and corrupted all the indices globally of, because this, there was like a gossip system, so this stuff propagated all around, and there was one packet transmission in one place that got corrupted. The CRC check still worked, and the entire storage system went down. All the data got corrupted. Any other questions? Yeah.
So in the context of designing systems for NoSQL databases, sometimes you have to choose between block storage, instant storage, and something like EFS that's distributed. It sounds like you're recommending that you just run tests and see what kind of performance you get out of each of those before you make a decision. My concern would be that sometimes the performance might be inconsistent based on who else is using the systems or what boxes you get, that kind of thing. Any recommendations for generating data that is consistent and reliable?
Very good question. Yes, so there are actually a whole bunch of very good questions wrapped up in that one. So the one is how do you get consistent data in a virtualized environment? And I guess one reasonable example is just to run many of them. So if you launch, don't just run your tests once, automate them, launch, 100 virtual machines in 5 data centers if you're using a particular vendor, public cloud, and measure all the data and see, get a proper statistical evaluation of what the performance range is. The other thing you can do is there are specific instance types which explicitly have unshared, like local disks. And again, I mean, don't trust them. Go and measure them in 5 different data centers and make sure that you actually get consistent results. So that's, right at the bottom, understand what the actual virtualized or otherwise hardware is that you plan to run this thing on. And then, I mean, just incrementally, I think your question was related to like layering stacks of storage. So right at the bottom, you might have a block store or file system, and on top of that, did you say you're building a key value store or database? Start at the bottom, make sure you understand what the underlying layer looks like, and then try and measure each layer independently. So measure your database, let's say, on a local disk, and see, we understand exactly how the local disk works. When we layer the database on top of it, this is what happens. Now we understand what the distributed block store looks like. We've measured across all the data centers, across all the different instance types. Now we layer it on top, and we make sure that what we see makes sense. And I think, that's the only way. And the shorter answer is pay someone else to do that. Like, data storage as a service is a thing. There are lots of smart people who've done all this stuff for you. There are many cases, depending on the size of your business, and exactly, there are a mix here today of vendors and users and all sorts. But pay somebody to do that stuff. Like, unless you're actually a storage vendor, just buy a service.
Okay, I think we can all give Quinton a big round of applause for kicking off our day with a great keynote. I was live tweeting it. I hope you're at Quinton Hoole. At Quinton Hoole. Okay. Otherwise, some other Quinton Hoole's been tagged on. Okay. Excellent.